Hello, everyone. So if you remember last time, we used the second moment method again to derive a formula for threshold function of a balanced graph. So basically the idea, if I want to summarize it, was that, to show existence of a particular type of graph, we can look at the indicator random variable or sum of some indicator random variables. And if we show that that sum is positive, means at least one graph exists of a particular type. Now, in order to show that, because we're looking at the asymptotic behavior, if you remember, as we were looking at g of n and p, and we wanted to know as n goes to infinity, what happens. So in order to show that, let's say limit p of xn bigger than 0 equals 1, which means that xn is bigger than 0 asymptotically almost surely. Well, we saw that we could look at the limit of a particular expression. It was, if you remember, variance x over e of x the whole squared. So we defined a particular capital X, which, as I said, was sum of some indicator random variables. And to show that limit p of x bigger than 0 equals 1, instead, we could show that limit variance x over e of x the whole squared is 0. So this is called second moment method because the main technique or main trick was to look at that particular expression, variance x over e of x the whole squared, take limit, show it's 0. And when we talk about variance x, we are basically talking about second moment. Now today, again, we want to use the same method, which is second moment method. So today, we'll use, again, second moment method to estimate the clique number of g of n and p as n goes to infinity. So what was clique number, if you remember? So recall a clique of a graph G is a subgraph whose induced subgraph is a complete graph. So basically, if you have a copy of a complete graph inside your graph, we would call that a clique. And if, let's say, if you have a copy of a complete graph with, let's say, k vertices, we can say we have a clique with k vertices. Let's say if you have a graph, for example, you have a triangle inside it. So that means you have a clique with 3 vertices, and so on. What about a clique number? The clique number of G denoted by omega of G is the size of largest clique in G. So if you have a graph G that has a clique of size 5, means a complete graph, a copy of complete graph of size 5, or K5 basically, if it has a copy of K5, but it does not have a copy of Kn for any n bigger than 5. Then we say the clique number or omega of G of that graph is 5. Okay, so now we want to study omega of G for G equals G of N and P. And for simplicity, let P equals 1/2. So we want to fix P, let's say to 1/2, where all the arguments that we're going to make. Of course, you can apply it for other P values as well. But for now, let's fix P to 1/2. So one important difference so far with the argument that we have for G of N and P compared to last time lecture. In last time lecture, where P was changing, was a function of N. And for threshold function, you know, for example, triangle, threshold function was 1/n. So we said if P is much less than 1/n, what happens? And the graph would not contain a triangle, and almost surely. And if it's much bigger than 1/n, it would contain a triangle almost surely. But this time P is fixed. Let's say we fix it to be 1/2. And we want to look at the clique number of this graph. Of course, G of N and P is a random graph with n vertices, and each edge appears with probability P, in this case 1/2. So we can talk about clique number also in the probabilistic way, in a probabilistic way. So basically, I want to show that the clique number will be close to 2 log n, 2 log n in base 2. So in which case do I want to say that, you know, the clique number is close to that particular number 2 log n? So let's start with the theorem. Let G go at G of N and half. Then limit P, the probability that omega of G of N and 1/2 is bigger than 2 log n in base 2 is equal to 0 as n goes to infinity. So first we want to show that almost surely, asymptotically almost surely, the clique number of G of N and P cannot be bigger than 2 log n. Okay, proof. Okay, first let me start with the statement that I have here. Okay, let me show you with the cursor. Okay, so this expression is equivalent with saying that, so see omega of G of N and P, or N and 1/2, is bigger than 2 log n in base 2 if and only if. So when can I say that, for example, let's say clique number of a graph is bigger than 6, for example. When can I say that the clique number is bigger than 6? The clique number would be bigger than 6 if the graph would contain a copy of K7, right? So if it contains a copy of K7, then the clique number is bigger than 6. And also conversely, if the clique number is bigger than 6, that means it has a copy of Kn for some n bigger than 6, such as K7 or K8 or K9 and so on. But if it has a copy of, let's say, K8, it will automatically contain a copy of K7 as well, right? So the clique number is bigger than 6 if and only if it has a copy of K7. So similarly, I can say that the click number is bigger than 2 log n in base 2 if and only if g of n and 1/2 contains a copy of k, let's say L, for example, for L equals ceiling of 2 log n in base 2. Well, 2 log n in base 2 may not be an integer. Let's say it's, for example, 5.6. This click number would be bigger than 5.6 if and only if the graph contains a copy of K6, the first integer bigger than 5.6. I just told you the argument for, let's say, click number bigger than 6, and then I justified from both directions that it has to have a copy of K7. Similarly, the click number will be bigger than 2 log n choose 2 if and only if, with providing this similar argument, we can see that it happens if and only if it has a copy of KL for L equals this number. Okay, now what can I say? When can I say that this happens? That it has a copy of KL? I can say this would occur if and only if, let's say, the events A1, A2, A sub L and choose L occur, where A1 is the event that the graph with vertices, let's say 1 to L, is complete. A2 event that it's a subgraph, right? Subgraph with vertices, let's say 1, 2, 3 to L plus 1 is complete, and so on. So let me explain here. So when can I say that I have a copy of complete graph KL? Well, in total, I have n vertices. So if I want to have a copy of KL, so either the subgraph with vertices 1 to L should be complete, or the subgraph with vertices, I don't know, 1, 2, 3 to L plus 1 should be complete, and so on. So how many choices do I have to have a copy of complete graph KL? Well, I have to choose L vertices out of n vertices, which is, so number of choices is n choose L. So that's why I'm saying here that in total, I have, let me show you with the cursor. In total, I have n choose L options. Okay, so note how much is P of each of these events. Let's say, for example, again, A1, the event that I have the subgraph with vertices 1 to L is complete. How much is probability that A1 occurs? So see, for example, let's say 1 to, say, all the way to L. So if this wants to be a complete graph, that means I have to have an edge between any two vertices, right? Otherwise, this would not be complete. So I have to have edge between any two vertices, which means every possible edge should appear. How many possible edges do I have if I have L vertices? So I have to choose two vertices out of L vertices. How many options do I have? So L choose two. And each edge would appear with probability 1/2, right? You still remember we're talking about G of n and 1/2. That means every edge appears with probability 1/2. And for, let's say, for example, A1, I need to have an edge appear between vertex 1 and 2, another edge between 1 and 3. And in total, I have L choose 2 options to choose my edges with vertices 1 to L, and all of them should appear. Each one appears with probability 1/2. So 1/2 to power L choose 2. So what I said can be also applied for the event A2 and also other. For I between 1 to n choose L. Thus, okay, now see, I want to, again, let's look at the goal. I want to show that this limit of this probability is 0 as n goes to infinity. So forget about the limit part. First, we're going to simplify the expression for probability, and then we can take the limit and show that as n goes to infinity, the limit is 0. So P of omega of G of n and 1/2 bigger than 2 log n in base 2 is same as P of, we just established that this would occur if and only if A1 occurs or A2 occurs, or A sub and choose L occurs, and this one by union bound. Again, see, we applied a similar technique last time, if you remember. This is less than equal to sigma P of AI. I from 1 to n choose L, and each of these P of AIs we said is 1/2 to power L choose 2. Now this is less than equal to n to power L over L factorial times 1/2 to power L times L minus 1 over 2, right? Using, so n choose k. Well, sometimes for n choose k, we need upper bound n to power k. But of course, it's not only is less than n to power k, it's also less than n to power k over k factorial. And this guy, 1/2 to power L choose 2. L choose 2, of course, is L times L minus 1 over 2. And now what do I know about n? See, we knew that L was sealing this guy. So what does that mean? So that means L is bigger than or equal to 2 log n choose 2. And that means L over 2 is bigger than equal to log n choose 2. And that means n is less than or equal to 2 to power L over 2. Right? ceiling of a number is bigger than or equal to the number itself, so L is bigger than or equal to this. So divide by 2, I'll get L over 2 bigger than or equal to this. And this means 2 to this power, L over 2 is bigger than or equal to this number, which is N. Okay, so N is less than or equal to 2 to power L over 2. 2 to power L over 2, so this is less than equal to, so N is less than equal to 2 to power L over 2. So 2 to power L over 2 to power L divided by L factorial times 1/2 to power, so L squared over 2 minus L over 2. So 2 to power, now let's simplify this. This is 2 to power L squared over 2 times 1/2 to power L squared over 2 times 2 to power L over 2, right? 1/2 to power minus 1/2 to power minus L over 2 is same as 2 to power L over 2 divided by L factorial. Now this guy times this guy is 1. So the answer is 2 to power L over 2 divided by L factorial. This is the upper bound for the probability. Now, what happens now? Let's take limit. Limit, we want to take limit as n goes to infinity. As n goes to infinity, what happens to L? Well, of course, L goes to infinity as well. Right? What was L? L was ceiling of log 2 log n base 2. So, of course, as n goes to infinity, L goes to infinity. So, since L is equal to ceiling 2 log n in base 2, as n goes to infinity, we can say L goes to infinity. So limit 2 to power L over 2 over L factorial as L goes to infinity is 0, and limit P of omega of G of n 1/2 bigger than 2 log n base 2 is equal to 0 as n goes to infinity. So remember that this guy here, 2 to the power L over 2 over L factorial, was an upper bound for this probability. So as n goes to infinity, which means L also goes to infinity, the upper bound goes to 0. So the probability also goes to 0 as n goes to infinity. Okay. So now, second part of theorem, or another theorem, I can say, let's give it, call it another theorem. Let let's say epsilon bigger than 0, less than 1/2, then limit P of omega G of n 1/2 bigger than 2 minus epsilon times log n in base 2 is equal to 1 this time as n goes to infinity. So almost surely, now let's say, for example, if epsilon is 0.01, for example. So asymptotically, almost surely, I can say that the clique number of G of n and 1/2 is bigger than 1.99 times log n choose 2. So clique number is bigger than 1.99 times log n choose 2. But if I jump to 2 log n choose 2, we just showed that asymptotically, surely we can say that the clique number is not bigger than 2 log n choose 2. So there is a cutoff here, right? So until any number before 2, like let's say 1.9 times log n choose 2, click number is still bigger than that. 1.999 times log n choose 2, click number is still bigger than that. But once you reach 2 log n choose 2, the click number will be less than that. Okay, so can you imagine like what type of behavior like this click number would have? That is a number that is less than 2 log n, but bigger than 2 minus epsilon times log n for any positive epsilon. Well, for example, you know, one function satisfying these conditions, I'm not claiming that click number is this function, but just to give you an idea, if you are wondering how come, you know, click number is less than 2 log n, but bigger than 2 minus epsilon log n for any epsilon positive. So for example, let's say if you consider 2 log n minus, let's say, root log n, or minus root 2 log n, doesn't matter. So look at this function. Well, first of all, it's obviously less than 2 log n. And it's bigger than 2 minus epsilon log n for any epsilon positive. Because so look at the term that is deducted from 2 log n is root log n, which is a term lower in smaller power or lower than 2 log n itself, much smaller than 2 log n. So it has it's of a smaller order, basically. It's of a smaller order that compared to log n, but this one is 2 minus epsilon log n. So what is deducted from 2 log n is epsilon log n, which is bigger than root log n. So the deduction here is more compared to 2 log n. So that means this whole term becomes smaller compared to this term. Of course, for large enough n, right? Because let's say if epsilon is very small, this may be in the beginning, the deduction could be smaller if the coefficient is small. But as n goes to infinity, the deduction here, because this is of higher order, log n compared to root log n, ultimately, as n goes to infinity, the deduction here would become larger. So, for example, click number could be 2 log n minus root log n, because it satisfies both conditions. This is, of course, one possibility. So we can have, so there are functions satisfying these two conditions that I said. Okay, now let's go back to the proof of this theorem. So proof okay, so this number 2 minus epsilon log n, again, I can this time, I can work with the similar notation we used in the previous theorem. If you remember, we worked with some number L, which was ceiling of 2 log n. So this time I can set L to be, so set L to be this time ceiling of 2 minus epsilon log n. Okay, then we saw that this condition would hold if and only if g of n and 1/2 would contain a copy of KL. Okay, so, and we saw P of omega of G of n and 1/2 bigger than 2 minus epsilon log n choose 2 is same as P of, let's say, A1 union A2 union A sub, let's say, n choose L. And this is same as P of, let's say, sigma xi, I from 1 to n choose L, be positive, right? Where xi is the indicator random variable for AI. Well, I'm interested to know whether at least one of these AIs would occur. Well, if one of these AIs occur, that means the indicator random variable for that is 1. So at least one of these AIs would occur if and only if at least one of these XIs would be positive, and at least one of these XIs are positive if and only if the sum is positive. Which is the idea that we used previous times as well, to show existence of a triangle. For example, we consider different indicator random variables, and then we looked at the sum of those indicator random variables to find out when the sum would be positive. Okay, so now if I call it X, this guy here, so let X equal sigma xi, I from 1 to n choose L. I can call it xn, let's say, because it depends on n. So we will have, then we will have limit p of xn positive as n goes to infinity equals 1. If this is exactly what I need to show, right? I want to show that this limit is probability is 1, which is same as this, and I call this term here, I call it xn. So I want to show that limit p of xn bigger than 0 is 1. And again, the whole idea of this topic, which is second moment method, is that we can, instead of showing limit p of xn bigger than 0 equals 1, we can instead show that limit variance, right? Variance xn divided by e of xn squared as n goes to infinity equals 0, right? Okay, so we just need to prove this and we would be done. Now, to prove, so let me call this one star to prove star above. So what is variance xn? Variance xn, we know it's variance. What was xn? It was sigma xi. Variance sigma xi means sigma covariance xi xj and sum over I and j. Again, if you remember, if I put extra condition that I is not equal to j, then I need to add variance of individual terms to this sum in order to get the variance of the sum. But if I don't put any condition on I and j, sigma covariance xi xj would give me the variance of the sum, because when I don't put a condition, that means I is allowed to be equal to J, and covariance xi same as variance xi. Okay, now we need to bound this term. Next, recall that covariance xi xj is 0 if the set of vertices for ai and aj have no common element or have one common element. If they have no common element or one common element, then AI and AJ would be independent and the covariance would be 0. We saw this before. So we would be, again, the similar idea that we used last time. Okay, now we would be interested in the case that we have two events with T common elements and T is at least 2. In that case, covariance could be non-zero. So let's assume the set of vertices of AI and AJ have T common elements with T bigger than or equal to 2, and of course less than or equal to L. Remember, each event AI is the event that we have a we have a copy of complete graph KL. So each AI has is a event for occurrence of a subgraph with L vertices. Complete graph with L vertices. So each AI corresponds to L vertices. Now, if I intersect 2 of them, could be T common elements, and T, well, T could be any number less than or equal to L, but if it's 0 or 1, the covariance will be 0, so we would have no issue in that case for bounding the covariance if it's 0. And if T is at least 2 and less than L, let's see how we can bound the covariance in this case. Okay, so covariance in such a case, covariance xi xj is expected value xi xj minus expected value xi times expected value xj, and that's less than or equal to expected value xi xj. And again, xi and xj, each of them indicate a random variable. They're 0 or 1. So this would be non-zero. This expected value would be non-zero only if both xi and xj are 1. And in that case, I would have 1 times p of xi equals 1 and xj equals 1. Again, these are similar ideas to what we did last time, if you remember. Now, when can I say that xi and xj are both 1? If ai and aj both occur. Okay, now AI occurs. When can we say AI occurs? AI occurs if we have a complete graph, a copy of complete graph KL with certain L vertices, and similarly for AJ. And what is the probability that they happen? So basically, if AI happens, I need to have a complete graph KL with how many edges. So because it has L vertices and it has to be complete graph. So let's say I have L vertices here, and I need to have, let's say, one edge between any two vertices. So in total, I need L choose two edges to appear here. And also for the other one, so let's say this is for AI and this is AJ. Again, you know, L vertices. So again, L choose two edges, right? So how many edges in total? This plus this, so that's going to be 2 times L choose two edges I need to appear, but I'm assuming they have T vertices in common. T vertices in common between these two graphs means how many edges in common. So T vertices, I have T choose two edges because again, it's complete graph, so I have one edge between any two vertices. So if there are T vertices in common, there are T choose two edges in common. So in total, I have this many edges, but T choose two of them are common edges, so I have to deduct that. So minus T choose two. So this is the number of edges that has to be appeared in order to AI and AJ both occur. And each edge, I'm assuming it appears with probability 1/2. So 1/2 to this power. So this probability is 1/2 to power 2 times L choose 2 minus T choose 2. Okay, so this one is for any fixed xi and xj, where I'm assuming that xi and xj are indicator random variables corresponding to ai and aj, and ai and aj have t vertices in common. Well, now in how many ways can I have two ai and ajs with t vertices in common? So now that's the next question. So now there are how many ways to have two AI and AJs with T vertices in common. So first of all, for AI, remember AI has L vertices out of N vertices in G of N and P. So first I have to choose L vertices out of N vertices. Now, once I choose my L vertices, I have to choose T of those L vertices to be common vertices between AI and AJ. So then I have to choose T vertices out of L vertices to be common vertices. And once I do that for AJ, I am left with, basically I have to still choose L minus T vertices for AJ out of how many vertices? But I had N vertices in total, L of them were already chosen. So I still have N minus L options to choose, and I have to choose L minus T of them that are going to be the vertices, the non-common vertices of AJ. The L vertices for AI, T vertices in common. So I have to choose T out of L vertices. And then L minus T non-common vertices for AJ out of N minus L vertices that are left for me. So covariance, okay, now for each fixed xi and xj, this is the bound. And so I have to sum over all such xi and xj's. And what am I gonna get? So variance x, which was sigma covariance xi xj, sum over I and j. So this is so less than equal to, remember this was the bound, so less than or equal. Okay, so this is less than or equal to. Now if we have, if t is fixed, then there are this many ways to choose AIAJ. And for each of them, the covariance is bounded by this term. So for each fixed t, I have to multiply this number by this number to get the upper bound for this sum. But then t can also, of course, change. Well, we said for t equals 0 or 1, covariance will be 0 because of independent events. But t can change from 2 all the way to L, right? So this is less than or equal to sigma t from 2 to L. And then this number, which is n choose L, L choose t, n minus L choose L minus t, which is, as I said, number of ways to choose ai, aj with t common vertices, times 1/2 to power 2 times L choose 2 minus t choose 2. Okay, now we have to bound this term, of course, divided by e of x squared. So now next, we will bound variance x over e of x the whole squared in two cases. So case 1, if t is bigger than or equal to, less than or equal to L over 2, and t changes between 2 to L, I want to divide this sum to two parts, from 2 to L over 2 and from L over 2 to L. So in this case, let's see how we can bound our sum. Okay, so note, okay, first of all, please remember that this is the bound, this sum here is the bound for variance x. Now I have to divide this by e of x squared. Now what is e of x? Now e of x, we already calculated above e of x, if you remember in the previous theorem, where we calculated sigma pai, but because x is sigma xi, so e of x means sigma exi, but each exi, because in expected value of indicator random variable is pai, right? So same as sigma pai, and we already calculated that. It's n choose L times 1/2 to power L choose 2. Well, in the previous theorem, our L was, I think, chosen a little bit differently, but still same idea, same concept, and same formula for expected value x, which is same as sigma pai. This time our L is different, but still I can use the same formula. So it's n choose L 1/2 to power L choose 2. N choose L 1/2 to power L choose 2. So variance x over e of x squared is less than or equal to, now this number divided by this number, so n choose L, there will be one n choose L in denominator, because in denominator is e of x, which is this expression to power 2. So 1 over n choose L. 1/2 to power L choose 2 to power 2 means 1/2 to power 2 L choose 2, which cancels with this term that I have here. So what will be left? Times L choose t is left, n minus L, L minus t is left, and 1/2 to power minus t choose 2 is also left. Okay, now this one is less than or equal to L to power t over t factorial. First of all, see, let me show you this term here, L choose t is less than or equal to L to power t over t factorial. And then I have what other term? So n 1 over n choose L. So that means times 1 over n times n minus 1 to n minus L plus 1 over L factorial, right? So I can write L factorial in top. And then times this guy here. So this guy, I can write it as n minus L times n minus L minus 1 to n minus 2L plus T plus 1, right? And divided by L minus T factorial, and then times 1/2 to power minus T choose 2. Okay, so what am I gonna get here? Now, let's try to regroup these terms. Let's say if I regroup this one with this one together. So that will be L times L minus 1 times L minus T plus 1, which is less than or equal to L to power T as well. So then I'm gonna get another L to power T here. So it's going to be L to power 2T divided by T factorial. And then so this guy here, so in this top, okay, let me show you. This guy is less than or equal to n. This is also less than or equal to n. So this is going to be less than or equal to n to power. How many n's do I have here? It's going to be L minus T. L minus T terms. And then divided by, well, this expression that we have here, n times n minus 1 to n minus L plus 1. And then we have 1/2 to power minus T choose 2. I can, of course, write this one as 2 to power T choose 2. And then this is less than or equal to L to power 2T, N to power L minus T. Now this denominator, well, T is at least 2, so this guy is at least, T factorial is also at least 2. And then, so this one is of order N to power T, sorry, N to power L. This is of order N to power L. And then times T is at least of order 2n to power L. So it's going to be bigger than or equal to n to power L. So let me write this is less than or equal to n to power L for large enough n, right? So for large enough n, this is at least n to power L times 2 is bigger than n to power L. So, but it's in denominator, so I have to say this is less than this numerator divided by n to power L, and 2 to power T choose 2 is less than 2 to power T squared over 2. So this one, if we simplify, we get L to power 2T divided by n to power minus T times 2 to power T squared over 2. And then if I simplify this, okay, now let's see what we know about n. We know L was less than 2 log n, if you remember. L was, in this case, ceiling of 2 minus epsilon times log n. So let me show you again. This is L, ceiling of 2 minus epsilon log n. So it's less than 2 log n. And then this one implies that L over 2 is less than log n base 2, which means n is bigger than 2 to power L over 2. So n to power minus t, because power is negative, is n to power minus t is in numerator here, or which is same as 1 over n to power t, right here. So n to power minus t will be less than 2 to power L over 2 to power minus t, which is same as 2 to power minus L over 2 to power t. So if I plug back, I can say that variance x divided by e of x the whole squared is less than L to power 2t times 2 to power minus L over 2 to power t times 2 to power t squared over 2. And I can write this one as L squared times 2 to power minus L over 2 plus t over 2, the whole thing to power t, which is less than L squared times 2 to power minus L over 4, right, to power t, using t is less than L over 2. Remember, in case 1, we're assuming t is less than or equal to L over 2, so t over 2 less than or equal to L over 4. And this one will be less than or equal to L squared times 2 to power minus L over 4. Now, as n goes to infinity, L goes to infinity as well, right? Remember, let me write down again. L is ceiling 2 minus epsilon log n base 2. So epsilon is fixed, of course, and as n goes to infinity, L goes to infinity. So L squared times 2 to power minus L over 4 goes to 0, right? Exponentials, of course, are dominant and over polynomials. And so what can I say about this term now? That's if we set q equals L squared 2 to power minus L over 4. So variance x over e of x squared will be less than or equal to sigma q to power t, t from 2 to L, which is less than or equal to sigma q to power t, t from 2 to infinity, of course. And this one is what? By geometric sum formula, q squared over 1 minus q, which goes to 0 as n goes to infinity. Because as n goes to infinity, q, we said, goes to infinity. It goes to 0, right? Q is this guy. Q is this guy, which goes to 0 as n goes to infinity, which also means L goes to infinity. And therefore, this upper bound goes to 0. So we are done with case 1. Now case 2, if t is between L over 2 to L, okay? Now how can we bound the sum in this case? In this case, note that e of x, which is n choose L, 1/2 to power L choose 2, right? We had this formula for e of x from previous theorem, and we also used it once during proof of this theorem. So this one will be bigger than 1 for L. Our L was, if you remember, 2 minus epsilon log n choose 2, the ceiling. And for large enough n. So you can verify this yourself as an exercise, that for our choice of L, E of x, which is this expression, we already showed this, is going to be bigger than 1 for large enough n. Okay, so thus it is enough to show that the limit variance x over E of x over E of x as n goes to infinity is 0. Because E of x, remember we want to show variance x over E of x squared has limit 0, but in E of x for this choice of L is bigger than 1. So if we show variance x over E of x has limit 0, variance x over E of x the whole squared will be a smaller number, and therefore the limit of that number will be also 0. And to do this, how can we prove this? Now let's look at the expression we had for variance x. So variance x was L choose T. Was the sum of, if we go back, see this one here. Now L choose T, n minus L, L minus T. There was n choose L as well, n minus L, L minus T. And then times 1/2 to power, I think it was 2 times L choose 2 minus T choose 2. And then divided by E of x. E of x I wrote it right above here, n choose L. 1/2 to power L choose 2. And of course there is a sum over T, if you remember. Well, because if you remember, there was a sum over T, where T was changing from 2 to L. Now we already consider 2 to L over 2 as case 1. Now L over 2 to L, we are in case 2. So let me say the sum T from L over 2 to L, because we are in case 2. Okay, now if we simplify, this cancels with this, and this also simplifies the 1/2 to power L choose 2. So this is less than or equal to sigma T from L over 2 to L. L choose T, n minus L, L minus T, 1/2 to power L choose 2 minus T choose 2. Okay, and then this is less than or equal to L choose T. We can say it's less than or equal to L to power. Well, first I can write this one as T from L over 2 to L. L choose T same as L choose L minus T, like basic property of binomial coefficients. And this is less than or equal to N choose L minus T, and then 1/2 to power L choose 2 minus T choose 2. So this point we use the fact that, if you have, let's say, N choose K is less than or equal to M choose K for N less than or equal to M. Well, this one you can easily see why this is true, because, N choose K means what? Means like N times N minus 1, N minus K plus 1, divided by k factorial. Now, if k is fixed, so as you increase n to m, let's say, denominator is still same, numerator increases, so the whole fraction increases. So this one is obvious. So here, if you compare, well, L choose T and L choose L minus T, of course, they're equal. And N choose L minus T, and this one, N minus L choose L minus T. So this one is bigger than equal to the previous one because N is bigger than equal to N minus L. Okay, now I can now use the fact that remember that, you know, n choose k is less than equal to n to power k, right? It's a basic property of, again, binomial coefficients. And this one, so the first term is less than equal to L to power L minus T. Second term, n to power L minus T. And the next term is 1/2 to power, but L choose 2 means L times L minus 1 over 2. So L times L minus 1 over 2 minus T times T minus 1 over 2. So this is less than equal to NL to power L minus T, and then times 1/2 to power L squared minus T squared minus L plus T, the whole thing divided by 2. Okay. Now I can write this one as NL times 1/2 to power L plus T over 2 to power L minus T. So L minus T times, so this is going to be NL to power L minus T, 1/2 to power L squared minus T squared over 2. And then I have to also include minus 1/2 as well, so that I can also get this term, minus 1/2 in the power. Okay, now what do I know about n? So n was, okay, let's look at what we know about n. We go back to the definition of L. In our theorem. Here. So L is ceiling 2 minus epsilon log n choose 2. So L is bigger than this, which means L is bigger than 3/2 log n choose 2. Because remember, epsilon was a number between 0 and 1/2. So that means 2L over 3 is bigger than log n base 2, which means n is less than 2 to power 2L over 3. So n is less than 2 to power 2L over 3. Okay, based on the choice of L that we have. N is less than 2 to power 2L over 3. And L means 2 to power log L choose 2. And this one means 2 to power minus L minus T over 2 plus 1/2. Now if we simplify further, so then we get, so this is 2 to power log L choose 2. So plus 12 over 3 minus 1/2. So that's going to be 1 over 6. That's going to be plus L over 6 minus T over 2 plus 1/2. And then the whole to power, of course, L minus T. Now, what do I know about T? T is between L half and, well, of course, there was still sum as well. I didn't write the sum, just for simplicity, but if you want, you can write it. Okay, now T changes between L half to L. So what can I say about this guy here? Okay, now T is bigger than L over 2. So that means minus T over 2 will be less than minus L over 4. So this is less than or equal to sigma T from L over 2 to L. 2 to power log L choose 2 plus L over 6 minus L over 4 plus 1/2, then the whole to power L minus T. And then L over 6 minus L over 4. It's 2 to power log L choose 2. So that's going to be minus L over 12 plus 1/2 to power L minus T. Now again, if I set this one to be, let's say, Q, similar to the idea used in the previous example, I mean, part of proof, previous case. So then we have limit, so let me say it this way, that as n goes to infinity, L goes to infinity, like what we saw, and Q, which is 2 to power log L choose 2 minus L over 12 plus 12 goes to 0, right? Because the power goes to minus infinity. So see this term here goes to infinity, this goes to minus infinity plus a constant. So plus is 1 over 2, not 12. But of course, you know that this term is dominant over this, so it's 2 to the power minus infinity, which goes to 0. So what do we have now? Okay, so upper bound will be less than or equal to sigma q to the power t, t from 0 to infinity, which is 1 over 1 minus q, right? It's some powers of q. So of course it's less than or equal to the whole geometric sum, which is 1 over 1 minus q. And this is because q goes to 0, so this is less than or equal to, let me say 2, for example, for large enough n. Now q of course depends on L and L depends on n, so for large enough n, 1 over 1 minus q will be less than 2, and therefore as e of x, which is n, again we had this expression before, n choose L, 1/2 to power L choose 2. But previously we said it's bigger than 1 for our choice of L. But in fact, you can prove something stronger. You can show that this goes to infinity for our choice of L, which was, if you remember again, ceiling of 2 minus epsilon log and choose 2. Again, verify. So you can verify this one. Once you verify this, of course, it will be bigger than 1 for large enough n, which is the previous claim that we made. I also left this one for you to verify. So you don't basically need to verify this separately, just verify that it goes to infinity for our choice of L. And once you verify this, now what can we say? Therefore, as this, so variance x over e of x the whole squared, which is 1 over e of x, so less than equal to 1 over e of x sigma q to power t, with the choice of q that we had here, right? T from 0 to infinity, and this is less than equal to 2 over e of x for large enough n, because for large enough n, this sum was less than 2, and this goes to 0 as n goes to infinity, because e of x goes to infinity as n goes to infinity. And that's it. So we separated the sum. Of course, this was in the case, this sum here, this upper bound is the upper bound for this term, variance x over e of x the whole squared, when t is between L over 2 and L. So this term, we found the upper bound for this term, and we divided into two sums, and each of those two sums we showed it converges to 0, so the upper bound for this goes to 0 as n goes to infinity, which was exactly what we needed to show. So we basically proved that the clique number of this random graph G of n and p, if you consider 2 log n in base 2, the clique number will be less than that, asymptotically almost surely. But if you consider like 2 minus epsilon times log n in base 2, again, asymptotically almost surely this time clique number will be bigger than 2 minus epsilon log n choose 2, but less than 2 log n choose 2 log n in base 2. Okay, well, that's all for today. Thank you and see you again.